Let's focus on any and sum. As I said earlier, summing argument is syntax sugar for generic, so arguments of opaque type uses within table by default. Also, any and sum arguments are specialized by Swift compiler's optimizer. We found any and sum are specialized by optimizer in some example. However, we need to note the limitations. For example, in different modules, any is not specialized regardless of the inlineable attribute. How code is optimized depends on the Swift compiler's implementation, and it is kind of black box out for us. So it can be said that we need to use appropriate sum and any regardless the specialization. Okay, so hello, I'm Yuki and I'm from Japan. In this session, I'll talk about the deep side of sum and any. You will learn sum and any, how the sum and any work at the usual Swift language and the deeper side of compiler. This is today's agenda. First, I'll introduce the Swift evolution related to sum and any. It might be helpful if you are not familiar with them. Second, I need to talk about the existential container which related to any to describe the cost of it. In the end, let me introduce how any and sum are optimized by Swift compiler. Let's start from exploring any and sum evolution from Swift 5.7. In this session, the keywords any and sum are important. And any is keyword for using existential type, and sum is for using opaque type. First, let me tell you what an existential type and how any is used and it evolved. Let's take a look at example of existential type. In this source code, there's a definition of shape protocol to represent concept of shape, like rectangle, triangle, and more. You can implement them by conforming to the shape protocol. And you may want to use them in abstraction based on shape protocol. In this source code, we would like to have a variable that can assign any value which conforms to shape. And as you know, you can use shape for type annotation to achieve it. By this annotation, we can assign rectangle to the variable and triangle. If there is a protocol type in type annotation like this, the entity type is called existential type. In this source code, part of shape annotation is existential type. A variable with existential type receives any value which conforms to annotated protocol. From Swift 6, we need to write any keyword as a prefix of existential type. But why did Swift need to introduce it? Existential type is implemented by a technology called the Existential Container. This container has a mechanism to receive any value of protocol. The detailed mechanism will be talked later, but Existential Container has a performance cost when reading the value and calling function from inside of the container. So let's think if there's any keyword like this code. If we want to understand the performance cost of this, and we cannot understand whether shape is class, struct, or existential type at the first sight. So if we have any keyword here, we can understand this shape is existential type and the consider performance at first sight. That's why any helps us when reading a Swift code. Let's see the other evolution. Existential type is now very useful when you're using a protocol with an associated type. This protocol P has an associated type which named A. If your protocol has associated type, we could not use it with existential type before. From Swift 5.7, we can use protocol with any keyword regardless the associated type. Let me introduce additional evolution. This protocol P has an associated type named A as the previous source code. Now, we can use the new feature named primary associated types for the protocol with associated type. You can write the type parameter as protocol statement for representing associated type, but how we can use it? primary associate type was introduced to Swift standard API, and let's take a look how to use with correction protocol as an example of primary associate type. Before Swift 5.7 rewrote generics code with the where keyword when we want to add constraint to associate type element. If you want to reduce the context of generics, you can use any correction for erasing type. However, any correction is wrap abstract, so it may have a performance cost when using. Now, you can write that constraint in lighter and smarter way by primary associate type. This code specifies into elements, and you can specify the associate type's constraint by assigning the type variable. This is more clearly than the generics. Let's go back to the code. Protocol P. By primary associated type, you don't also need to write the where keyword to add constraint to extension. Also, you can define a variable by using primary associated type. We don't need to write boilerplate code for a type region like NEP. Now, existential type is more useful. However, as I said, we still need to pay cost for existential container. Next, let me introduce some with opaque type to solve it. As I said, any keyword makes P existential type, and it requires the existential container. Now, you can use opaque type by writing some keywords not to use existential container. To understand why existential container is not used with opaque type, we need to know how generics working. Existential types use various information in container to abstract by protocol. However, generics don't use a container, and the type variable keeps concrete type information and uses it for abstracting inside of function. In fact, Swift compiler compiles opaque type in argument to generics. In other words, the left code and right code are almost same. And opaque type in argument is syntax trigger of the generics. That's why an opaque type in argument doesn't require existential container. However, how about an opaque type in return type, which named opaque result type? How is it treated, and why is it is introduced? To understand opaque result type, we need to understand that Swift has two ways to think about protocol abstraction: type level abstraction and value level abstraction. Type level abstraction is achieved by the generics and opaque type. They are trying to abstract function and variable by using concrete type information. As I said, generics keeps concrete type information by the type variable and use it for abstraction. Value level abstraction is achieved by the existential type. Existential type variable is trying to abstract functions and variables by erasing concrete type and treating values as an underlying protocol type. Until Swift for type level abstraction is achieved by generics, and value level abstraction is achieved by the existential type for argument. But about return type, value level abstraction is achieved by the existential type. However, type level abstraction is not achieved. So what is going on? Let's think how to abstract return type of this function. Let's try to return P import class which conforms to P protocol. We want to abstract this return type. First, let's use the generics. It looks like that will go well at first, but we have a problem. The concrete type or P type is decided by user of this function, so it becomes compile error due to type inconsistencies. You can also make compile pass by using unsafe kits, but it makes untype safe API. Yes, we can use any instead, but we still need to pay cost for existential container. How about set return type as preamble? It will not pay cost of container, but it opens functions implementation too much. If engineer use this function in many places, it will be a nightmare. If you change return type of function to other type, compile errors are shown in many places. The user of your function needs to fix all of them, and it's very painful. To solve the type level abstraction for return type, reverse generics was suggested at first. The syntax is not the same with the normal generics because the type variable definition is before the return type. If we use this method with reverse generics like this code, the return type is treated as special type, which means some type conforms P. The special type abstract return type, but it has concrete type information, so we don't need the container. Now, the concept of reverse generics is introduced by opaque result type from Swift 5.1. The some P treated as the special type by compiler, no generics. But you can access variables function related to P protocol. Now, we can fill the table like this. Opaque type contributes to abstraction and performance for return type. I'll talk about any and some evolution in regard to abstraction. This part was helpful for understanding about important point of any and some. Next, let's focus on how existential type works by existential container. This part is helpful to understand existential type's performance. Let's take a look at the shape protocol code again. As we have seen, existential type uses existential container, and by container mechanism, existential type variable can hold any value conforming to protocol like triangle, rectangle, more. Also, variables existential type will accept any object regardless the object size. If we take a look at the differences of size between existential type and normal type, we can learn the secret of existential container. Let's take a look at this code. Triangles and a big curved rectangle conform to the shape protocol. A big curved rectangle type has more variables than triangle. Let's check size of these two objects. You can investigate the object size by memory layer.size function. Triangle is 8 bytes and big curved rectangle is 16 bytes. Next, let's check the size if they are in existential type variable. And the size is increased, and exactly 40 bytes if they are treated as existential type variable. So let's take a look at the bigger type, very big rectangle. As you can see, the object size is 48 bytes. However, it becomes 40 bytes if it's treated as the existential type variable. So what is going on? To describe this, I have to talk about how the existential container accepts struct values regardless of different sizes. Let's take a look at when we are trying to assign small struct objects to existential type variable like triangle. First, the size of existential container for struct is 40 bytes on the 64 CPU. That's why the memory layout.size function indicates the 40 bytes. Regardless the protocol type, existential container has 3 buffers inside the container, and each size 64 bits. This buffer holds the value inside of struct. If you use a 32-bit CPU, the buffer size is 32 bits. Triangle object holds only 2 objects, and size of each object is same or less than the 1 buffer size. So each object in triangle is copied to each buffer in the container. So how about big object like very big rectangle? First, an existing container allocates additional heap area in memory, and the address of heap object is stored to first buffer. Next, all objects in very big rectangle are copied to the heap area. That's why an existing container can hold any size of object. Normally, using and allocating heap space performance is lower than the normal struct usage. At first, very big rectangle looks like only 40 bytes for container. However, there is allocated heap area allocated by the container in memory. As I have seen, the existing container has a mechanism to assign any value into container, and it has performance cost. Next, I need to talk about the method dispatch. Existential container has an information named protocol witness table for method dispatch. What is it? In Swift, there are two kinds of witness table named value witness table and protocol witness table related to the existential container. Value witness table has an information of type. For example, this table knows how to allocate, how to deallocate, and the size and slide as memory layout of the type. Every type has this information. Protocol witness table has information that how to call protocol methods. Let's take a look how to use it. Let's explore a triangle type again. Shape protocol now has function named draw, so we need to implement triangle.draw. Triangle's protocol witness table is generated as type information if protocol has a function. This table maps the protocol function to the conformed types implementation. In triangle protocol witness table, shape.draw is mapped to triangle.draw. Triangle's protocol witness table is assigned to container when value is assigned to container. Next, let's see what happens when we call draw function from existential type object. First, protocol witness table is referenced, and the implemented function is searched from the table. We can think like that witness table is a dictionary, and shape.draw is as a key of the dictionary. Next, triangle.draw is found as implementation for draw function, and it is called correctly as draw function. Determining which function to call at runtime like this way is called dynamic method dispatch. Generally, there are two ways of dispatching methods in Swift: dynamic dispatch and static dispatch. Dynamic dispatch determines the function to call at runtime. For example, existential type variable declared with a base class as type method related to Objective-C are using dynamic dispatch. Static dispatch determines function to call at compile time. For example, struct global function in extension is decided by static dispatch. The runtime cost of dynamic dispatch is higher than the static dispatch, and it is a disadvantage of using existential container. Finally, I introduced the metadata. Metadata is a record of type information. It contains value witness table, which I talked previous topic. Every type has metadata. The container gets it from object. The total size of all buffer is 24 bytes, and protocol witness table and metadata information need 8 bytes each. Adding this size is 40 bytes, which is what I see. Let's summarize what we learned. First, existential container size is fixed real rest of type, and it is 40 bytes for 64 CPU. Next, existential container uses buffer to store object, and allocates heap if object exceeds buffer. Next, the way of existential container method dispatch is dynamic dispatch. In this topic, we learned the mechanism how existential container implements existential type and its cost. Let's look a little deeper side than the Swift language to learn the existential container behavior more. Swift has intermediate language which named Swift intermediate language. This intermediate code explains how existential type actually work. Our Swift code is compiled to Swift intermediate language code before becoming an application. The code is mainly used for optimizing our Swift code. The intermediate language code explains with a lot of information hidden from normal Swift code, like reference count and window step and more. And we can see how existential type works from the intermediate code. Let's see how this code is compiled to the intermediate code. You can generate intermediate code by using this command. This is generated intermediate code. The code in each line is named instruction, and it looks difficult and complex. But don't worry, I'll take a look only necessary information. First, this is generated protocol with a table of triangle. This first file indicates the information about shape protocol's draw function. Right part has a function symbol indicates the triangle's draw function. It looks like protocol function draw is mapped to triangle's function draw. As I said before, this information is used for the method dispatching. Next, let's focus on the code which uses existential container. The intermediate code above is same as the Swift code below, and they are initializing variable and calling a function. Let's focus on the initializing existential type variable first. First, this code tries to allocate memory area for global variable. Next, this code calls initializer to create triangle object and assign created object to variable named %4. In next code, there is a init underscore existential underscore addr instruction. This instruction for existential container and assign address to variable named %5. And triangle object %4 is assigned to address %5 with metadata and the protocol witness table. As you can see, initializing existential container is explicit in the intermediate code. Next code is calling draw function from the existential type variable. Let's see how it works in intermediate code. First, this open underscore existential underscore addr is loading existential container and assigning information to %7. Next, this witness underscore method instruction tries to get draw function to call from witness table in loaded existential container. This yellow part is specifying shape protocol draw function. In generated protocol witness table, there is same item or yellow part. So the symbol of triangle draw in light item is passed as information or function to call. Triangle the draw is now obtained as a function to call and assigned to %8. Now, function in %8 is called with loaded existential container %7. This is the actual code doing dynamic dispatch with existential container. What about the variable that is not existential type? I take a look only function call as an example of static dispatch. In this code, the triangle draw function symbol has already been embedded in the intermediate code. As you can see, the static dispatch searches function to call in compile time. Also, we can investigate intermediate code about opaque type. Unfortunately, due to presentation time, we have to skip this part. However, you also can explore the secret part of Swift. Please enjoy by command and enter the. Please enjoy by this command to enter the intermediate language world. In this part, we understand any mechanism with Existential Container and its performance cost. Finally, let's explore how compiler optimizes your any and sum. This is the draw function, and it has argument abstracted by generics. The draw function of argument object is called inside of this function. Let's see how this function is compiled to intermediate code. This code below is result of compiling. I omitted the unnecessary code for describing. As you can see, witness table is used here. This witness method instruction is not using Existential Container, but it tried to get the protocol witness table from the type variable t. In fact, generics uses a witness table by default if Swift compiler doesn't optimize a function. If you pass the optimization flag to Swift compiler and there is a use case of function, Swift compiler generates the function with specialized argument. Let's see with the draw function with use case by triangle object. If you compile this code with optimization flags, the specialized version of, is generated by compiler. Analyzing function symbol reveals that this draw function's argument type is fixed to triangle. Also, within this function, the within table is not referenced, and the method dispatch is static. As you can see, specialized function has concrete type. This helps reduce cost of dynamic dispatch by witness table. Let's see how optimizer works with several modules. Now, draw function is public in module A and which is used by module B. Inside of module A, draw is called with triangle objects, so specialized draw for triangle is generated. However, for use case in module B, specialized draw is not generated. What is happening? It should be noted that there is a limitation that function arguments may not be specialized. As we have seen, if use case in different modules, specialization is not done if you don't open the implementation as an interface. If you want to enable function specialize, add the inlineable attribute to open the implementation as interface. There is another attribute called specialize, and it may also help you. Let's focus on any and sum. As I said earlier, summing argument is syntax sugar for generics. So arguments of opaque type uses witness table by default. Also, any and sum arguments are specialized by Swift compiler's optimizer. Let's take a look example of any with use case of triangle. Swift compiler generates specialized draw function by triangle type. This specialized function doesn't use witness table and existential container. We found any and sum are specialized by optimizer in some example. However, we need to note the limitations. For example, in different modules, any is not specialized regardless of the inlineable attribute. How code is optimized depends on the Swift compiler's implementation, and it is kind of black box out for us. So it can be said that we need to use appropriate sum and any regardless specialization. This is a summary of this section. First, existential type, opaque type, and generics are specialized by compiler. However, we need to use appropriate sum and any as possible because how code is optimized depends on the compiler's implementation. Now, I talked the other section of this. Let's recap what I talked today. First, I talked an existential type and opaque type evolution with type level abstraction and value level abstraction. Next, we understand how Existential Container implements Existential Type and its performance. And in the end, I talked about how our any and some code is optimized. If this knowledge can help you maximize your performance of your Swift code, I'd be happy. Yeah, and as an appendix, I listed any and some evolution which I cannot introduce today. Please check them if you are interested. And also, this session will help you to understand with API design with today's knowledge. Please take a look if you are interested. Also, please see these talks to learn more, and Leo will talk about practical usage of generic keys in unit testing tomorrow. And I talked about the detail of the Swift compilers optimizer in NS Spain 2020. Okay, so if you have any question, please ask me freely on Twitter DM or directly speaking. But because my English listening skills is low, so please talk to me a little sorry. But yeah, thank you for listening to this session. I'm happy to deliver this talk from Japan. And yeah, I want to say thanks to the Kohi, who is also of the heart of Swift, and Katei Nogakun, who is a Swift compiler specialist and engineers and interpreters in LineCop, and supported many Swift, supported the Swift team who supported my travel. And I want to say that my mother, because today is my mother's birthday. Yeah, thank you.